That's like kind of weird because
You might hit or an adult. That's like.
All right. Let's bring it in. Let's bring it in. So,
yeah, we're ready now.
let's talk probability, density, and mass functions.
How does mass functions?
We're going to find out.
Aha.
I'm glad you asked.
I didn't.
Consider an experiment that measures a random variable. We learned about random variables last time. I know last time was like a little longer ago than maybe you would like, because I know you guys missed having class and all that, but we're back finally. We can plot the relative frequency of the measurand, which is the random variable, in different bins, which we say bins in quotes because what they mean are sort of ranges of values. So we would say, for instance, if we were measuring the voltage, one bin might be between 1 and 2 volts. That's a bin. We toss it in the 1 to 2 volts bin. And maybe there's a 0 to 1 volts bin. And who knows, maybe if you're lucky, there's even a 2 to 3 volts bin. Did I say that right? No, I did not.
Every time you say bins, I'm just thinking Legos. I'm sorry.
Bin.
I'm thinking about laundry. I'm thinking about laundry.
Yeah, it's basically what I'm talking about, so that's great. Yeah. All right, so when we do this, it's called a frequency distribution or a probability mass function, PMF. Consider, for instance, a probability mass function as plotted in figure 4.3 down here. So we have ourselves a measurand. So say it was like some voltage, okay? And it was a random variable. It was moving around kind of randomly, and we were measuring it. And we just tossed them in these bins. So tossed them 0 to 5 bin, 5 to 10 bin, 10 to 15 bin, and we can see the relative frequency here using this bar plot. So we call each of these AIs, so the heights of each of these bars, we would say that's an estimate of the probability of that random variable landing in that bin. Okay, so over time, if you measured enough of them, part of why we're doing this is to determine what we mean by enough of them. If we measure enough of them, we could start to say, okay, well, the probability that it lands between 0 and 5 is whatever the height of A1 is, assuming that we've normalized this so that they all add up to 1. So what you do is you require that the sum over I of the AIs is 1. Okay. And if we had a finite number of bins, K is the finite number of bins. So I equals 1 to K. If we wanted to do it out in all of its glory. So for instance, in this one, what is the probability that you have a voltage that's between 10 and 15 volts? Yeah, approximately a third, right? It's approximately, so it's whatever this height is, which looks to be about a third. Okay. The frequency density distribution is similar to the frequency distribution, but with each of those bar heights, AI, being divided by some delta x, which is the width of the bin. So if we said in this graph, delta x is what? Five. Yeah. So that's if we divided each of those heights by delta x, then that would be the frequency density distribution. If we let the bin width approach 0, we derive the probability density function. So if we let delta x go to 0 and k go to infinity, meaning that we sum up an infinite number of bins and our width gets smaller and smaller, so that we're talking about a smaller and smaller interval here. Then what we have left over is called the probability density function. We typically think of a probability density function f, like the one in figure 4.4 on the next page, as a function that can be integrated over to find the probability of the random variable or measure n being in the interval between a and b. So here is an example. We'll talk more about it in just a moment. But this is what the probability is between a and b. So the probability that the random variable x is in the interval a to b is the integral of the probability density function, PDF f, over x. So if you look up here, the probability that x is between a and b is the integral of the function, where the green line is f. There are a couple constraints on this. The probability density function, f of x, can never be negative. So there's that. And, I mean, if you think about it, that makes sense, right? Because if you had it, say it like right here, it actually dipped below 0. And then if you asked, what is the probability that you end up in this interval here? You'd end up with a negative number for the probability, which like doesn't have any real meaning to it. It's what we call an imaginary I'm just kidding. It's not. I made that up.
So see, I've taken statistics. I don't remember that.
Yeah. There's no thing called the imaginary probability. I just made that up. Nobody write that on their midterm exams or their final exams. Imaginary probability.
I'm actually going to be on a television interview, and I'm going to say that, and I'm going to quote you.
Ooh.
And then tell people your website. It's as simple as just read
Yeah.
it.
Well, then what I'll do is I'll link to this explaining not to do that. And then I'll walk away and just be like, clearly people understand nuance on the internet, so it'll be easy to explain.
I'll just say it's fake news.
Are you mad at me, Jordan?
Maybe.
I feel like you're mad at me. It's like harshen my mellow, man. Harshen my mellow. Harshen my mellow. You never heard that expression? It's a good one.
Wait, what? You
Yeah, it's a good one. Apparently you haven't had enough of me harshen your mellow yet, so...
I won't lie, that sounds a little wrong.
I mean,
Normally I'm not mellow as a general rule.
everything sounds a little wrong if you wanted to.
But all I know is that some feathers have been ruffled in the past few days. That's as far as it goes.
I come into class and joke, but I do know that like my name and swear words have been in the same sentence a lot lately, and like I understand that. That's okay.
There might be a folder or two titled on my computer.
Yeah.
Let's
That's
continue. Just not
So, not to linger on hating on me,
Weird. Integrals of
we integrate over the probability density function, the PDF, to get the probability that the random variable shows up in that interval. Okay? So, of course, if we are going to have a probability distribution that is valid, if we integrated over the whole interval, so if we wanted to know the probability that x is somewhere on the interval from negative infinity to positive infinity, That's going to be equal, by definition, to the integral from negative infinity to positive infinity of f of x, or we should use a dummy variable here, f of fancy x, which is, it's the Greek letter, I think it's pronounced C, but everybody pronounced it differently. No, wait, no, that one's chi.
Yeah.
That one's chi. C is the, not that. I was exaggerating, and it's like that one. It's like the double loop one.
That's what I usually for Zeta.
Yeah.
Oh, you do Zeta.
Zeta is like that. I used to just do this, but then when I became a professor, I was like, I need to learn that. So Zeta is like this. It's kind of fun to write.
Also, side note, are we getting into chi-squaredness or?
We could, maybe. I don't know if we're gonna have time. Probably not, because I want to spend more time on t-distribution and Gaussian. We're gonna introduce Gaussian a little bit today, and then I don't want to get too hung up on stats. Like, I want to do as much stats as possible. A few of you have taken stats, which is really helpful for you because it's probably just gonna all be review, which is good. But for those of you who haven't, this is like your stats, so I don't want to short you on it either. So I'm gonna make sure you get it. Because part of, this class is instrumentation and experimental design, which I'm meaning to change the name eventually because I really don't like. Experimental design is like, it's like, are you designing in an experimental way? Or are you designing experiments? It's not clear. So, all right. If you integrate over the whole thing, what do you guys think you need to get? 1.
Well, we got the answer right in front of us.
Oh, you guys. You guys. You're so ahead. Head of the curve. I like it. We now consider a common probability mass function, PMF, and a probability density function, PDF. So the binomial probability mass function. Consider a random binary sequence of length n such that each element is a random 0 or 1 generated independently, like this. 1, 0, 1, 1, 0, etc. down at the end, 1, 1. Let events 1 and 0 be mutually exclusive and exhaustive, meaning you can't get a 2. Also, you can't get both 1 and a 0. You either get a 1 or a 0, or then there's nothing else you could possibly get. You have to get one or the other. So when I say it this time, I actually mean it. And the probability of getting a 1, let's assign a variable to it, p. Okay, so this is like 0.3 or something, but I'm going to call it p for a moment. The probability of the sequence above occurring is, and I just feel like you guys already know the answer to this, and I don't even have to tell you, but so the probability of getting a 1, then a 0, and then a 1, and then a 1, and then a 0, and then
It's funny because it's supposed to be random, but so far as I can tell, it looks like you've actually got a series.
yeah,
It's supposed to be random.
it's supposed to be random.
Essentially, it could be random.
I came up with it just by button mashing. P times 1 minus p. So p is the probability of getting a 1, right? If they're independent events, we can just, the probability of getting any sequence is to multiply the probability of each value repeatedly, right? So probability of getting a 1 is p. Probability of getting a 0 is 1 minus p. Because if you don't get a 1, you get a 0. So probability must be 1 minus p to get a 0. So then probability of getting a 1 is a p, and then probability of getting a 1 is a p. Probability of getting 0 is 1 minus p. And multiply them all the way down. And then the last one, we end with p and a p. And that is my probability of getting that sequence. Okay? There are n choose k, so this is the function n choose k possible combinations. So I'm not going to get too much into that function, but we often will write it in this sort of vector form here with an n above and then k. What this is that there are n choose k possible combinations of k1s for n bits. Okay? And that exclamation is not just me emphasizing things. That is the factorial function. And I think that you guys all know the factorial function. What? Nice. In 345? I mean 305?
Yeah.
Nice. Did you guys use a recursive function? Nice. Did you have fun?
No.
Could you use a loop?
We did use it.
Okay.
It's best not to ask if you have fun during MATLAB.
You guys,
I'll spare you
I just need to start enjoying MATLAB. I don't know what it is. I don't know if you like, give you like a tap. Oh, I know, a keg in the CAD lab.
Okay,
That
we're talking like an actual cake?
actual keg.
Okay.
And you get tokens based on how much successful code you have written.
So I would not get any.
So have you ever heard of
Sir?
have you ever heard of the Balmer Peak?
No.
No.
This is the thing. So this is this axis is number of drinks, beers or whiskeys, preferably. And this is effectiveness
So what, like alcohol content?
at coding.
No, effectiveness
Oh, okay.
at coding.
And it goes something like this. Whoop.
Really good. Just shoot straight up to perfect.
And they call this the Balmer Peak after, I believe it is the Balmer of Microsoft.
10 drinks in, you believe all your
I don't really even know the story behind it, but supposedly this is the Balmer Peak. Somewhere in here, everybody's got their Balmer Peak, where after like maybe a drink or two, you're like perfect, you're like hitting your zone, and then as you continue, it just goes downhill.
I think Jeff.
We need to put this under study.
Yeah,
No, I proved this weekend. That's 2 drinks for me.
yeah.
I think mine was 3.
All right.
Some of us are underage.
And then some of us
Don't
get to hang out at the Balmer Valley.
Yeah.
Yeah. No. Anyways.
Some of us try and shoot for that hashtag over there.
What was that?
What?
Over here?
Yeah. It's like driving real hard and fast.
That's imaginary effectiveness.
We can always plot it on a logarithmic plot so that
10 to the third.
you know, never quite get down to zero.
That's how we hear of the Erin Valley.
Yeah. All right, so we better keep going. Okay. N choose k possible combinations for k1s for n bits. Of k1s for n bits. Therefore, the probability of any combination of k1s in a series is n choose k times, so the k1s show up, so you have to have, notice that in this sequence here, we had, of the visible ones, we had 1, 2, 3, 4, 5 of them, and 1, 2, 3, 4, 5 p's showed up, right? So p is raised to the k, the number of ones, and 1 minus p is raised to the total number of values, so ones and zeros, minus the number of ones. And this gives us the binomial distribution. Okay, it's called the binomial distribution. And this is a typo, so good thing you came to class. This is a PMF, probability mass function. I know, right? If you didn't come, you guys wouldn't have known that.
Never would have known.
Oh, and look at this over here. Well, yeah, it actually works as distribution. Okay, so consider a field sensor that fails for a given measurement with probability P. Given n measurements, plot the binomial probability mass function as a function of k failed measurements for a few different probabilities of failure. Okay? And guess what we're going to do?
MATLAB.
Live and in MATLAB, we're going to do this. And you guys are starting to, MATLAB's becoming your friend already. You guys are like, you know how most relationships start off and it's like, wee, and then like, you know, it's like that called like the honeymoon period?
Where was my honeymoon period with MATLAB?
No. I was going to explain. This is for a normal human relationship. This is for the MATLAB. So I'll write like human
Or just regular?
and MATLAB.
We're gonna need
It goes like this.
I'm calling bull.
I don't think the slope is that fast. I don't think the slope is that quick.
I think we need an inverse logarithmic where the closer to 0 it is, the far closer it is to 0.
See, now I think that's pretty accurate, but you need like really like delay. Your time constant's huge on that rising.
I
Okay.
think my relationship with MATLAB started like one where you get assigned a partner at the beginning of the year and you don't know that person and you find out that you're just completely incompatible and you just spend the entire year fighting. That's what MATLAB is. So that honeymoon phase never happened.
I'm like, hey guys, let's
Hey,
plot
can you
this.
do
And
this
MATLAB's
thing?
just like,
Tell me what to do. I did
wrong
tell you
number
what
of
to do.
variables.
Correctly.
Incorrect
Tell you
input
correct
values.
Syntax error. Syntax error.
What's up, MATLAB?
So let's think high level.
Not the right.
We're really just plotting, right? That's all we're doing. We're plotting this function. Okay? So that's what our goal is. Plot that function for different values of k. So one axis is going to be k. And then the other axis is going to be f. We're going to want to plot that plot for different values of p. For like 3 different values of p. So let's focus first off on writing this thing to do it for one value of p, and then we'll expand it with our features. So like get something to work and then iterate on it. That's one good way to approach this. So let's say, first off, you guys seeing this okay? I think I can. I think I have to do like.
It's just on your, go to your homepage and hit default layout.
No, like in the script, like make the text bigger. Because you can change the text like Arial.
No, that's what it is. It's your layout is changed to where it's split into 2 pages.
Fonts.
You get like one big command window and one big script window.
Yeah, so it's a little bit.
Right. So it's just your layout function. It's just like go home and then layout default.
Woo!
Whiff.
All right. Clear.
Close all.
Close all. That's a good way to start a script.
We know this so
CLC,
far.
CLC.
Bam. This is a cell. If you do 2%, it's a cell. And then if you hit Command Enter or Control Enter on Windows, it just runs that cell. Pretty nice little thing. I like it. Let's talk parameters in this one. We've got, let's just say first off that our probability is just going to be like the first one, 0.04, is that what I said? And then let's do n. So n is the total number of values in the sequence of 1s and 0s, right? Let's do like 100. And k is going to vary, so that's really all our parameters, I think. Can't really think of anything else right now, so we can go back if we need to. And then let's construct the binomial function. Let's do that one first. So let's do one of these nice so-called anonymous functions. Anonymous. F, we'll call it. And it's going to be a function of n, k, and p. Okay? So the, and I have no idea. Let's do, I'm guessing it's like binomial? Well, there's an example, but I don't really want the example. Okay. Oh, well, that's very helpful. I don't want an example. Let's do doc binomial. That will search the documentation for binomial, and then look, it's MuPad. It's MuPad, we don't want MuPad, that's the symbolics. N choose K. There it is. Binomial coefficient for all combinations. All right, so we could do like binomial of like 4 choose 2. Wait, no, it was n choose k. Sorry. N choose k. Look at that. Bam. Okay. So that's what we want. N choose k. And we're going to do n and k. So that was the first term in our function, right? So, boom, n choose k. Now we need to do p to the k. So times p to the k times 1 minus p to the n minus k. Bam. I don't know, it seems reasonable. I feel like it'll work. Any objections to that? All right, so there's our binomial function. I know we should, back in our parameters, we should define our k array. I like to use this underscore a when I'm making an array. So what? So we want to go, well, let's do a linspace because we have no reason to do a log space. Let's do a linspace. So the syntax is the lower bound, upper bound, and then the number of values. So we are going to start at 1. We want k to be equal. You got to choose 1 at least, and then up to let's do let's do n times 100, and then let's do n of them. So it's just going to go, n, we'll just do n, and then n of them. So, no, it's going to go from 1 to n with n steps.
Got it.
N is the number of values, not the step. I think I might have said it wrong. Okay, so that gives us, and if we're not sure, we could always be like, linspace gives it to you as a 1 by n, but, so anyways, I printed it out, and I see all of these things, but if I wanted to see it a little bit nicer, I would do k, a, that's transpose, and that would show me the column of them. Whee! Okay, so I'm just hacking along here, just slowly constructing things and checking them as I go, because otherwise I will screw up. So, then I want to do let's just do the plots, man. Let's do the plots. So the first thing, figure plot. Let's do our KA, and we want to do f of KA. And this isn't going to work the first time, but let's just do it anyways and see what the error is that happens. So first off, let's save it on the desktop, and we'll call it Binomial Jordan. And we run it. And it's generally, I know you guys probably like, should I add path, change folder? Usually change folder is the best route. There. There's an error in binomial Jordan.
Sorry.
Okay, so line 16, the error is not enough input arguments. Okay? What did I do wrong?
KA isn't really defined.
It's an
function,
anonymous
is it?
Well,
function
no,
that
the
takes
F
3
is a
inputs.
function of 3 different variables.
Ah!
Variables.
Okay. N is one of the inputs, so C it has 3 arguments. So N is one of them, K is one of them, and P is one of them. P we define. So that is better. But notice that KA, we're putting in a whole lot of values. Let's just put in, just to like see if it'll, well, no. So let's do this. Let's plot this and see if it'll plot. I'm guessing it's going to still throw an error. Why do you guys think it'll still throw an error?
Is you're using K sub A.
Not too many input arguments because it's going to receive an array for.
So KA is an array, and it's
Yeah.
maybe not ready to handle an array.
Yeah.
And so it throws us this error. The second input has to be a non-negative integer. And choose K. Okay? So now, so this is like, I mean, you kind of knew this was going to happen, but I kind of wanted to show you, like, okay, we're constructing this and we run into these issues. How do we handle them? So when we don't use something like N choose K, if we just had this, we would still run into a problem. And it's going to tell us that our dimensions don't work because we're multiplying matrices together here. And we didn't say take each element of the array and do element-wise operations. So it would have a problem with that. But we could easily fix it in that case. But with N choose K, I don't know. Maybe you can use some vectorized version of N choose K, but I'm not aware of one. So when I run into stuff like this, I just say, okay, let's just evaluate f. So I'll do f a at each value, and we'll have to put that in a loop. So for I equals ka, so each one of those k. So I'll just do, actually I'll do k. I haven't defined k at all, so I'll just do for k equals each of those values. Do this, end. So here's a little loop. So I'm going to, I mean, MATLAB kind of lets you get away with not initializing arrays, but it's better to initialize them. So how big is FA going to be? We're going to evaluate each value of k, right? Yeah, it's going to be 1 by 100. So, and one way we could do this, the easiest way to do it is to say, create an array of zeros, and then give it the size of ka, which is going to come back to be the size of ka, and then if we make another array of all zeros the size of ka, we're always going to have the same number of, same dimensions, which is convenient. I also, what I like to do, which is not something that you have to do, but it's a little more confusing looking, is to initialize an array with nans in it, because ones is just like zeros, and then if you do nan times it, it just gives you nan in every element. Then if you try to stick a value in for each element and you miss one or something, it'll be nan, and you're gonna see it. If it's a 0, you might not notice. I like that. That's a little idiom I use. But you know, if you use zeros, it's totally fine. So we want to assign, and MATLAB has this nice way of allowing you to assign the I'm actually gonna waffle on this. For I equals 1 to the length of ka, which is to say for each value of ka, I'm going to say k equals k a of I, so the ith value. And I'm doing it this way because I think that it's a little less confusing this way. You can do it the other way too. Then we'll say that the f of a, or fa of I, so the ith element of the fa array is going to be f of n comma k comma p. Now we have a k for this value, and we can evaluate it. And then we'll have our FA, and then all we need to do is just plot KA and FA, and by golly, it worked. I kind of want to do bar plot, yeah. That's what I'm talking about. That's cool looking. Okay, because this is, I did bar because there is a value for each for each integer k, so it kind of makes more sense than a continuous looking function. So that is our bar plot. You could change our probability. So if we choose probability of 0.04, then out of 100, then there's a much higher probability we're going to end up with very few ones, right? So if the probability of getting a 1 is 0.04, we can look at this and say, oh, the probability of getting, in a sequence of 100, n was 100, right? Of 100 values from 0 or 1, our probability of getting like 10 or less is like, that's most of it, right? We summed all these up. It would be like, these are all down here. These up here is like very little probability of getting this. It would be like some really rare event happening a whole bunch of times in a row. Because probability of it happening is 0.04, so that's pretty small. For it to happen that many times in a row, for it to happen even like 10 times in a row is like really, really rare, right? It's very unlikely that it would happen. Or sorry, not 10 times in a row. 10 times even in a 100 sequence. If you took that probability, what if we make it a half? So there's a 50% chance of getting a 1 and a 50% chance of getting a 0. What should that distribution look like? It should be symmetric, right? Because you have the same probability of getting a 1 or a 0. So
It should, in theory.
yeah. So symmetric about 50. So out of 100, I really should plot this only to 100. But you're most likely to end up here. The most likely event is that, or the most likely outcome is that you have 50 ones and 50 zeros. And then it's just like if you look at the probability distribution of some random room of people, if there was like no bias in the data, like for instance, if it was like a high-paying jobs convention, unfortunately this would be skewed. That was like my jab at sexism. You guys like it? I don't know. It's a nuanced stab. Stab with nuance. Yes, so
A little slow on that one. I usually get that kind of humor.
it's all right. Late afternoon classes, I never teach in the afternoons, and I hate teaching in the afternoons because it's really hard to keep people awake. Yeah. But yeah, so the probability of getting around 50-50 when you do 100 of them is kind of what you'd expect. It's going to be the highest, and then it's going to tail off. Like, it would be really weird if you had a really 50% chance. So this would be like you're flipping a coin, right? And out of 100 times, if you got like 65% of them were heads, if it was really a fair coin, like that's really there's not a very high likelihood that's going to happen.
But
Right.
the thing is, though, we can account for that by based upon if you learn how to flip a coin, so that it always lands on heads, or like if you roll it. Like when I used to play my dad at dice games all the time, we got so good at rolling the dice that we knew how we could roll in such a way to land on a certain score.
Wow. So if you could do that, then
Go to Vegas.
you should
One, go to
you
Vegas.
should go to Vegas, but also be fast. Run. But also, then it wouldn't be really. There's not really a 50% chance.
No.
So then you're skewing it, right?
Correct.
So actually, what it is you're changing this probability. So maybe probability of getting a 1. Say 1's desirable, but you guys can bump it up. So like maybe you guys can bring up like 0.7 probability of getting a 1. Then when you guys play this game, this is what the distribution would look like for you.
What is the 0.0102 scaling on the y-axis side of this?
So this is the probability of exactly a given number of ones being in the sequence.
Oh.
So the y value here, so 0.08. So see, I mean, we have so many different possibilities. They have to add up to 1, right?
Right.
So if you have more and more possibilities, this is gonna get smaller and smaller in amplitude for each one, but they always sum to 1. So this is like, 0.0849. Nothing is like super likely, but if you had to put money on it, you'd put your money on 70. 70 would be the number that you'd say, I know there's a 70% chance, and it turns out that 70 is the best estimate for it. It's the most likely outcome, is that 70 of them are going to come out to be 1s. So we'll introduce the Gaussian next time, but this is, yeah.
I feel MATLAB homework coming in our future.
But look at how it wasn't that hard though, right? Like I mean,
For you.
For you. Who's been working with MATLAB
Show
for a
us
long
A equals 5, B equals 3, C equals A plus B, C equals A, and then you ask us to do, make a while loop that parallel calculates the nodes of the neighbors of this fluid cycle.
that doesn't sound like this class.
He's mad at computational fluid dynamics. Let him vent. He's fine.
I don't need another class that I have math.